if you take, let's say 15 minutes in a presentation, we have 5 minutes of discussion.
Sounds
Okay,
good.
go ahead.
Okay, so hello, everyone. I'm John Castaneda. I'm a PhD candidate, NSF-VRT awardee a couple years ago. And today I'll be talking about characterization of light-activated microswimmers for controllable motion. So let's take a step back and look at what exactly microswimmers are, and they are a type of active matter. So what is active matter? Active matter is a large number of organisms, each individually energized in order to move or exert mechanical forces, or in my research, microparticles. So let's look at some examples of active matter that is more familiar. So on a macro scale, schools of fish, flocks of birds, these are all individually powered organisms that are moving in a structured and coordinated direction and moving with respect to their neighbor. So this is on a macro scale, but what I work with is on the micro scale level of microparticles in my lab. So they are swimming similar to the fish, but these are light activated, in particular with UV light. So when the UV light is off, they're undergoing browning motion. And right when I turn the UV on, they have some, they are activated and now propelled through their solution in a specific direction. So that is one of my goals. What I've been looking at over my time here is trying to control that direction of these guys in motion. So let's take a look at some examples of just basic microswimmers and how different changes to their morphology, their material, can all change their different motion as well as their different dynamics in the system. So changes to their shape, so having a sort of sphere, Janus-sphere shape with two different asymmetrical sides, with one hemisphere having some sort of coating and the other side of the Janus-sphere being totally different, giving rise to different chemical reactions. For this specific one, platinum, with material dependence, platinum and gold, different bimetallic semiconductor heterojunctions give rise to different electron transfers and give rise to different chemical reactions in our solutions, giving different sort of motions and propulsion techniques. And finally, just changes to the specific environment. So the pool that these guys are swimming in, whether it be changes to the aqueous solution, the external magnetic fields that I'm shining on them, or just different light excitations on them. So let's take a look at how I make these microswimmers. So the microswimmers first, and the main thing I use in my lab is all done with this physical vapor deposition system. So the main sort of tool that I work with is this guy, our electron beam. And when this thing goes wrong in our lab, everything gets shut down because this is the main thing that we're using. So before we get into the chamber, we got to start with the monolayer of seed particles. So what I'm working with is silicon dioxide seed particles, mainly ranging from 1 to 5 microns. And these are just factory bought seed particles, silicon dioxide seed particles. And I'm creating a monolayer on this silica wafer. So giving only one hemisphere in the field of view of our electron beam. So once I have that monolayer of seed particles, I'm then able to place these guys in my electron beam. Again, this is our special glancing angle electron beam, and you'll see why it's special with this glancing angle in a little bit. But it's also a co-deposition with the thermal evaporator system. So when we open it up, we place our wafer at the top, because this is all in a vacuum sealed chamber. So place our silica wafer at the top, place our desired material in our crucible at the bottom, and then we start a deposition process. And like I said, this deposition process takes place in a high vacuum sealed chamber. So once we get to that low pressure, below 1, around 10 to the -6, 4, we could start depositing. So here's just an example of a ionosphere of titanium dioxide. And the cool thing about our chamber is by just depositing more, we could create different shapes and structures. So here's just a ionosphere, sort of a thin film deposition. But when I deposit more and with the use of my glancing angle, so by me sort of changing the angle that substrate sample is being held on, I'm creating this shadowing effect to create these sort of tail-like structures on my microswimmers. And these, yes, so create these sort of tails, and once I create these tails, let's figure out how these guys move. So I want to control the motion of my microswimmers, and this is all the propulsion techniques that these microswimmers are undergoing is called self-diffusiophoresis. So that is basically just caused from photocatalytic reactions along the surface of the titanium dioxide microparticles that I'm working with. And so when these guys are in my aqueous solutions of hydrogen peroxide, there's creating an electron hole separation due to the photocatalytic reactions and giving chemical redox reactions of my fluid and giving fluid flow along the surface to give that sort of propulsion and make these guys move. So this is some work from a previous publication that I have from a few years ago where we looked at increasing the size of my tail lengths. How does directionality change? So what we learned was by me increasing the tail length, once you reach that sort of threshold or that length of the diameter of the seed particle, that directionality changes. So we're going from head first, and we could switch that directionality of microparticles to be head first. So rather than we going tail first, like it was originally with a little bit of titanium dioxide, by us coating more or depositing more, we're able to change that directionality. But by us coating more, we're changing that velocity as well as the direction that these guys are moving. So if this is with only titanium, what is adding some different metals to it? So that was my sort of next steps of looking at these guys is what happens when I add gold to just the tip of these tails and also the side of these tails. So you'll see why I chose to do the sides as well, or we chose to do the sides as well. So here's just some brief frame by frame pics of these titanium dioxide microswimmers. So they have this tail first motion and with few directions of motion, few freedoms of directionality. But when we add that gold, we're changing that direction. So instead of going tail first, we go head first, and we're no longer needing to deposit so much of that titanium dioxide. So we're able to change that directionality with only adding gold. So why is this? So the titanium interacting with that gold, there's an electron transfer going on with this semiconductor heterojunction on my microparticles. So those electron hole pair that's forming on that titanium dioxide is then jumping. Well, the electron is jumping to the gold and then sort of forming its own sort of redox reaction and causing that microparticle to switch directions. So if I'm able to switch directions by adding it to the tip, by me adding that sort of side gold part, I'm adding sort of a drifter. So I saw that directionality change, but I also saw a velocity change of about 1 micron per second by us adding that drifter. So I was also able to change the speed as well as the direction by adding another metal to my microswimmers. So some critical and forward thinking that I'm currently working on is coming from a lot of just the meetup program. So the meetup program is coming with the journal club and everything like that. The collaborations have been great. And one of the recent work before the collaboration was just coming from being experimentalist. So we got a publication earlier this year from where a lot of these things does not go right the first time, to where I'm in the lab trying to get stuff, trying to find the exact microparticle that I want to find, try to get the exact video, and they don't often work. But sometimes we find something that we weren't looking for, we weren't expecting. And that's what happened with this guy, where we were looking for something else, but then I noticed, well, we are seeing sort of this rotational motion along its axis for these microswimmers. So what's going on? Well, these guys are interacting with smaller microparticles, and that fluid flow along the smaller ones are causing the bigger ones to sort of rotate along its axis. So that gave rise to some good data and nice publication this past year. But what I'm working on now, and the cool thing is that I'm like really excited about now, is my nanostructures plus my microswimmers. So that's all in collaboration with Jen, Dr. Jen Martinez, and we're using her nanoclusters with my microswimmers. So instead of having bolt gold as another sort of metal to my system, I'm using atomically precise nanoclusters. And by me using these clusters, I'm adding sort of a more band gap selectivity for my microswimmers, giving rise to possibly changing the different directions on my microswimmers by giving maybe two different nanostructures, two different nanoclusters, that if I shine red light on one of them, it'll activate it, or if I shine blue light, it'll activate it and make it go a different direction, or that kind of thing. So that's what I'm currently working on. So in conclusion, morphology, environment, shapes, all affect my microswimmers and how they move and how they interact with their environments. And some future applications as far as my microswimmers can be looked at as it leads to future biomedical industry and programmable dispersion of medicine in the body and that kind of stuff with cargo delivery with my microswimmers. And finally, with my microswimmers plus my nanoclusters with Jen, we could hopefully push active matter research forward. And yeah, thank you.
Thank you, John. Questions? Yanka?
So you're adding, you can add more titanium oxide, but is there an optimum amount to add? I imagine if you add too much, it's too massive and becomes like non-rounding.
Right, yeah, so that's where this paper was, where we did a few years ago, where we were trying to find the optimal amount. So by us changing or by us adding more titanium, we're sort of increasing that velocity. If we just go from sort of a gynosphere to have a little tail, we increase from 2 microns to 5 microns. But by us adding more, if we reach that, if we just add a lot more, we sort of could change the direction. But also, if we just keep on adding more, we're adding more material, so it's less. It's adding more mass, which is changing the speed of my microswimmers. So that's where adding the gold was like sort of the next step, to where we didn't have to add so much of that bolt titanium, to where we could change our different structures based on what we're looking at.
On this, you said that you put gold and put a different spot and then it went faster or something like that.
Yeah.
But could it be more to say the surface area is a bit bigger as opposed to where you put it?
I think it has to do with the surface area, yes, because it does have to do with how much gold you're depositing on it. But I do believe it's the main thing about my microswimmers is that the morphology is or the direction that these guys are moving is all dependent on the morphology. So any little change, whether it be me depositing gold on the side, I'm changing the directionality, but I'm also decreasing the speed. And by me putting it on the tip, I'm changing the directionality, but I'm not changing the speed. So that surface area, and by me adding more gold, it could lead to honestly like nothing, because that interaction is already at that heterojunction between those two metals. So it's not necessarily like, that's where you kind of try to find the right optimal spot.
Okay, please.
Thanks, John. So my question has to do with the forward thinking. So when you're adding the nano clusters, is that also going to be done doing like the same physical vapor deposition?
No, no, that's a whole nother animal that
No, chemical
Yeah,
synthesis.
a lot of chemical yeah, the nanocluster has a whole chemical synthesis, but the deposition process of actually putting those clusters on my microswimmers, I won't tell you I know how to do it yet because I might not know how to do it.
Well, one expert in process is Dr. Wetten.
Yeah, the drop casting, like dry casting, is like the easy part to getting on the microswimmers, but honestly, like the looking forward of putting two different types of clusters on them. So trying to get these nanoclusters to stick to one side of my microswimmers and then somehow getting a new type of nanoclusters to stick to the other side. That's sort of like the yeah.
Jorge, the last question.
Thanks, awesome presentation. I had a question about the deposition of the gold on the tails. And then you have three, one without the gold, one only on the tip, and then one on the side. How do you determine that the gold is deposited only on the tip and that's actually not on the side?
Oh, so that's done with. I don't have any pretty SEM images on this presentation, but we do a lot of SEM and EDX characterization and imaging of my microswimmers. So we're actually able to see the different layering or like the different layers of my particles, as well as all these depositions are like done separately. So I'm able to do a whole deposition of titanium and then take those microswimmers out and do another day where I do titanium and gold. So I know all those samples are going to be uniform and all the same with the same type of gold or the same type of spot that I did them on.
And you can verify with us again.
Yeah, exactly.
Okay, well, John, thank you very much. And by the way, you have to do it with the TM because if you go to clusters, SEM will not.
Oh yeah, the for clusters. Yeah, the SEM ain't gonna work for the clusters. I know that.
Very good. So now the next presenter is Alex Lehr. The reason I asked Alex to present this is that he just went to a Gordon conference in clusters, by the way. It was atomically precise clusters. And as you know, in this Gordon conference, people is isolated. They have nowhere to go. So if there is something wrong with your presentation, they will tell you. And I got very good, reports for what he presented. Okay. So how do you? Okay.
No, you have to do it on your computer.
Do it on mine?
Yeah.
Okay. So that's why he's going to present what he presented in the Gordon conference in Ventura. Okay.
Okay. Well, that's not showing the right screens.
I think you probably view display settings. You want it to.
There we go.
Yeah, that should work.
Okay, I'm sorry, my presentation is not going to be nearly as polished as John's, but we'll get through this. I was going to spend the first part of this presentation talking about my fellowship, my scholarship. The deadline for this is coming up on December 1st. So if you wanted to apply for this, get it done now. It shouldn't, once you get the process going, it shouldn't really take you that long. I think the longest part be getting the letters of recommendations, because that depends on other people. But this is good for tons of different kind of STEM scholarship or STEM disciplines, and really anything you think of that's a STEM related. This is through the Department of Defense, and so they're looking for people that are smart to work for them. So some eligibility stuff, basic stuff to work for the government. I know the one that might be the biggest one for here is you have to be a U.S. citizen. So I don't know if everyone is or not, but if you are, apply. It's a great scholarship. The reason why this is so great is because it's full tuition, fees and everything, so you don't have to pay anything to the university. The annual stipend for PhD students is $38,000 a year, so it's much better than what the university pays you to be a TA or anything like that. The summer internship, so every summer you go and you work for whatever sponsoring facility or military base that takes you. If that place is farther away from your school address, which all of them are going to be far away from NAU, you get a summer stipend, so you get paid to go to that summer as well, so that helps a lot too. You also get a book in healthcare, so that pays for parking passes, new computers if you want to spend on that. Some of the facilities, if you go like an Army research lab or Air Force research lab, you can get good mentorship experience. You do end up working for the government afterwards, so that is something to think about when you apply. But kind of the way this works is you can apply and you have up until here. If you get it and you don't want to do it, you can still decline it. So there's no hurt in actually just applying. And then while you're in school, and then you work for them, and then after you're free to do whatever you want.
How long do you have to work for?
1-to-1. So every year they pay for school, you work for the government for a year. So.
But they pay you during that time, right?
Yes, and you get your normal benefits as a government employee, all that stuff. So you're just a full-on government employee at that point.
And they pay you like an employee, not others.
Yeah, they pay you like an employee. So having a PhD, I don't know if anyone has experience in the faculty with the GS scale or any of those scales. It's on the higher side because you have a doctorate. They're going to automatically put you at the higher pay scales. So that's kind of nice. You're not going to get paid $60,000 a year. You'll get paid much more than that, I imagine. But when you're doing that application, there's two parts to it, and Jorge could help with this a lot, but there's the personal statement and then there's the reason why you want it. If I'm remembering that correctly, it's been a while. But so the thing is you want that really good personal statement. And then on the other side of it, you really want to push why you want to work for the government. So having some good motivation there is something that'll make you stand out. Learning some of the trigger words with the government, like warfighter and things like that. Those make your application pop out too. So
Nice one, depends.
yeah, just learning trigger words for the government. They love those things. So one of the big things to look at is the sponsoring facility. When you apply, you can say, I want to work at these 3 places. Those will kind of be at the top of your list, but this is just as much applying for a job as it is applying for a fellowship, because you're applying to work at that place afterwards. So try to find some sponsoring facility, some military base or research lab that you like, that your interests are aligned with, and put that on the list and kind of tailor that towards those places so you kind of get what you want. And here it says you only need 2 references. I think you can have up to 4. I don't, but if you can contact someone at those sponsoring facilities and talk to them, that helps too. But yeah, it's pretty much like applying for all the other fellowships. Tell them who you are and be sincere about it. Make yourself stand out. So one of the things on here is November 16th, they're doing a webinar. It's the last one they're doing right before applications close. So if you're curious, I'm more than happy to send this to you. I just need your email address. And then you could sign up for it and you could ask questions and see what kind of application stuff that you want to do. So with that, I'll get on to much more interesting stuff with pretty pictures, talking about these nano alloys. So in our group, we're going to be working mostly with metals, mostly with kind of these middle metals of the pure table. We like to be able to use metals of different rows. I'll explain later, but that helps with imaging to be able to see contrast in different elements. And then also using cheaper, easier to get metals as well. Our main instrument we use is a transmission or electron microscopy. To give you kind of a quick rundown of how these work is you have an electron gun at the top, lenses that control the beam, they pass through your sample, and you get an image out the bottom. The nice thing with using electrons versus light is the resolution is much smaller. I think it's down to, I think we calculated like 2.5 picometers was something if you're using 200 kilovolts. So that's the theoretical. Microscopes haven't quite gotten there yet, but it's a little better than light microscopy. The one I use primarily is the STEM mode, where it's a scanning transmission electron microscope. So the main difference is your beam is narrowed down to a point and then scans across the sample. That has some benefits to it. Mainly, you can do multiple imaging while you're looking at the sample. The main ones being these bright field, dark field, and high angle. Bright field, obviously, you're looking at the sample, what electrons don't pass through the sample or get diffracted off. Those leave a darker area, and so your sample is darker, and that's what you see in your sample. Dark field is the opposite. You're looking at the electrons that are scattered off of the main beam path, so your sample is bright. The high angle is the very interesting one. That one looks at the electrons that were highly scattered off of your sample. And so one of the cool things you can do with this one is dependent on the number in the nucleus of your sample. So higher number of atoms, the more electrons are going to get scattered off. So the intensity of those spots is going to be higher. So you can kind of use that as a way to distinguish what elements are where in your sample. So that's a really cool one. Another one on here that's really kind of a cool thing to do that haven't used a whole lot, but we're trying to get into is this high or annular bright field. And instead of looking at the entire bright field area, you look at just the outer circle of that. And what you can do with that is you can actually distinguish carbon and oxygen and nitrogen if you have a good enough detector, so you can see where those elements are in your sample, and so you can see those elements, those atoms. Whereas the high angle, you can't really see those lighter elements very well. So when we're looking at these samples, we got to know what they're made out of. So in those microscopes, there's some different techniques that we do. The main one being this EDS, so X-ray dispersive spectroscopy. So we're looking at when the electron interacts with that sample, X-ray comes off, characteristic X-ray. You can use that to figure out what the element is. And so I have a line scan here of a gold, platinum, copper, and as it scans across that nanoparticle, you're seeing counts of the signal from those elements. So then we know that those elements are in that particle. We would love to use eels that should be 2 L's, not 2 E's.
That one uses the electron beam and it looks at the electron beam that's lost as it's going through the sample. And so very similar, you then can figure out what the elements are within the sample. And then, like I said, this high angle annular dark field is looking at the intensity of this. So you see spots that are brighter versus spots that are not as bright would be different elements. And then once we have these images, we got to figure out how the crystals put together. So it's a little bit of a matching game. So we have this beautiful particle right here. Now we're trying to figure out what that crystal structure is like. So Dr. Montecano was able to put a kind of a simulation together of matching up where these atoms might be in a little bit smaller version of this nanoparticle, but it's matching up to some of the other features that this has. And so now we can try to use the theoretical with what we're actually seeing and try to figure out exactly what the three-dimensional composition of these particles are. And so with this particle, actually, it's a gold, platinum, copper. What we're seeing is that the gold and copper are alloying together and the platinum and copper are alloying together. And so we're getting these different layers where it's going to be the gold and copper of one, the platinum and copper of the other. Another really powerful thing that I know Blake will touch on later is diffraction. So just like doing diffraction with anything else, you can do it with electrons. That diffraction can give you things similar to this. This is a fake diffraction, FFT image of these, but you can get these and then you can use that information to figure out what the crystal structure is, the spacing between atoms all the way through. Each one of these spots correlates to atomic spacing within that structure. So again, we're able to know that these line up with the gold copper and platinum copper spacings. And as you can see in this, you can see bright spots and dim spots, especially in this image where there's the brighter ones and the dimmer ones. So that would tell us where gold and platinum are, and the dimmer ones are going to be the copper. Another thing that we're seeing with these particles is that different size in the atomic radii is going to cause stress throughout that. And these particles need to relieve that stress somehow. And so one of the factors is that they create these twin boundaries and this five-fold symmetry in these particles. And this is very common among all the particles that we're seeing, especially when we're adding more metals. The prevalence of these twin boundaries is increasing. We're seeing it more and more. And so the idea is these are a way that these particles, these different atoms, are able to relieve some of that stress inside and what's going on. And so you can see a bunch of different kind of particles, all different compositions, and they're all very similar five-fold symmetry throughout. Using another software, and Jesus is really good at this, is geometric phase analysis. And this, you run the image through the software and you can see where there's differences in spacing of the atoms. And this is a great way to tell us if there's stress or strain, what's going on in here. And what we see is we're going through here, we're seeing kind of these areas of almost periodic compression and expansion between atoms in these nanoparticles. So it's really kind of cool to see this periodic, and it appears throughout tons of these nanoparticles on different areas. This nanoparticle with 4 metals in it, with doing this across these between the twin boundaries. Again, something almost periodic is going on with relieving that stress. And even with some of the small ones, again, between those boundaries, there's almost this periodic behavior going on within the particle. So you can't really see it within the particle, but just tiny, minute changes in the distances. So with that, kind of the group, Dr. Yakman with Jesus doing most of the heavy work at the synthesis. Also, Dr. Ramirez and Alondra in the group on the more Raman side, and then also working with Rob and Blake with different kind of electron microscopy.
Thank you. For Alex.
Okay.
There was a red box that you had on the periodic table of elements. Like, why are you only interested in those?
We have them. They're easier to get. They have some interesting properties. I know, so like gold is used for so much stuff. Very active for Talos as well as platinum. So I know using platinum in the particles, a lot of people interested in catalysis, working with collaborations to move out with that one. I know we've talked about branching off into some more exotic metals, but it's a matter of getting them and the price point and other things like that.
Another question?
Yes, I'm quite amazed. I didn't know you had access to Nigerian, Castaneda and Rhodesian. So, I'd love to get some from you.
It's
maybe.
It's an average square box. Coming from the physicist, it's how he makes things the most simply shaped.
Fair enough, fair enough. I do have a question about the stress in the alloy. Can you tell me a little bit more about that?
So and there's a couple different ideas. One of the ones is because the atomic radii is different, that could be causing this mismatch in the crystal structures, but also the idea of the bonding length between different elements is going to be mismatched. So as platinum is going to have a different bonding length between platinum copper. And as you add another element in there, that bonding length is going to be different. So that perfect, say just a cubic crystal structure is now going to be distorted in one way or another as those different elements are in there. And so it's just a matter of trying to find that in the entire crystal structure as it moves out.
Okay.
Images, most periodic, like displacements. For that one. I'm wondering, so these grain boundaries have any effect on the periodicity of the structure of those? What looks like periodic, like I would imagine that reduces stress of some kind.
Yeah, the grain boundaries are kind of a wall and they'll stop it. And so it kind of then resets on the other side.
But other than stopping it, it doesn't
Grain boundaries do introduce a little bit of a problem with this software because they're the software, you have to kind of play around with a certain area, it has to be perfect. You have to get a good FFT, and when you introduce that grain boundary, now you're throwing a lot of noise or other information into there. And so the software kind of breaks down on those boundaries. But the grain boundaries have shown to be, they themselves relieve a lot of stress from what it seems like. So.
Okay, Alex, well, thank you very much. And also another thing is, in the meantime, that of course, if you choose, let's say 10 elements, the number of combinations you do with 3 metals becomes infinite. Okay, so that way you have to be more. Like people are using machine learning to see all this works. Okay, now the next person I'd like to introduce is Blake Rogers. Blake, he got his master's in Arizona State University in Material Science. And I have to say that when we received the new electron microscope, we just got the room a few days before, totally full of a lot of things. So when the engineers came, they were absolutely crazy about how we are going to have this room ready for a microscope. And then Blake took over the problem. He did most of himself. I mean, even facilities said that they will take several months to do it. But he did it by himself, and then facilities just signed on. Probably the only thing they did is painting the floor. So it was amazing. So it was really incredible the work he did then. But also I have to say that besides being a great engineer and a great scientist, it's okay then.
Yeah, it's good. It just takes a minute.
Okay.
Sorry.
Yeah. So Blake is also he carries the card of Dr. Wetter. He's a tremendously good.
It should be good. Like if you go up.
And also, I have to say,
Oh, I gotta
the other day he shared with me some tamales. It's a fantastic cook. Really many. He's a man of many talents. Okay, so let me switch out the light. So,
Okay.
so you.
Is it good?
Can you switch the light to here? Okay.
Yeah, that's fancy. Well, if you start.
And by the way, the idea of break is that the microscope is a facility for APNS. You can use it, you're welcome to use it, so.
Go up to the top and share. We need to exit.
Bring your best samples. Bring your most.
Maybe go
difficult
to the Zoom and try it from
Like having.
Oh,
this connected.
there. Okay. And then share. Share screen? Yeah.
I'm sorry? No, but we can.
I think it's active.
It's just a fraction. Variables.
Oh, there we go. And then we want to share this guy, right? Yeah. Okay, and then start tuning. First.
Okay, okay, Black, thank you very much. Go ahead, please.
Sounds good. This is gonna be a lot more informal, maybe than the last two were. These are the only words on my presentation, so actually that might not be true. I did steal some slides from the internet. Because I wanted a picture of a field emission gun. Anyways, this is the Talos F200i. There's a nice little picture of it. I call it a microscope for the people because they try, but and a lot of the things that they've done to make it easier to work with, they've made it harder to work with. So I'm not sure if that's a good statement or not. Anyway, I'll just take you on a tour through the room real quick. This is walking in, you'll see. Here is liquid nitrogen that we keep. This is the high tension tank. So this is where we produce the high voltage that we use. A little scale so we can keep track of our liquid nitrogen. And then this is all of the computer equipment and various drivers and things that actually run the microscope. This is the microscope right here. So, come on. Okay. Yeah, that's good. A little bit more view, and then this computer's got like a lag to it. So there we go. And then I've got a sample prep station here for you. And then this is where we actually run the microscope from. This is the control board. It's like, there we go. Takes like 4 clicks to get it to go right there. Anyways, so yeah, we got the triple monitor set up. You can acquire images here. This is where you run the microscope. And then we can go back and look at the images that we've acquired on this side. Or we can use, there's a little network PC so that you can back up your files and stuff. We can also remote into that PC on this screen. This is the control board that we use for it. Basic thing, these are the most terrible buttons you'll ever face in your life. They're pressure sensitive, so you have no idea whether it's going fast or slow. And it takes a decent amount of pressure to get them started. So there's like no in between. It's just either all or nothing. And you're trying to do precise, Z height measurements. So one day I'm going to build my own board for this machine and we'll replace these worthless things because it's terrible. But the machine itself is great. If this thing will go. So this is a sample prep station. We got vacuum tweezers, little microscope so you can check out what you're doing. This is the single tilt. So it doesn't actually really do anything. It's all, we'll show you in a second. This is the double tilt holder. This one has a tiny little arm here. And so this guy can tilt like this, 60 degrees, which is actually pretty good. You can do a lot of stuff with 60 degrees. In fact, when we get into holography and all that kind of stuff, this double tilt holder will do what we need it to. So, okay, the vacuum system. I don't know how many of you have worked with vacuums. Dr. Yakman has got plenty of experience with them, and I'm sure he can tell you all kinds of horror stories about vacuum pumps, especially diffusion vacuum pumps with the oil and all that kind of stuff. We've kind of moved away from that with this microscope. In fact, all of the vacuum systems on this microscope are self-contained. So we have here a giant, this is the column vacuum pump. It's an ion gettering pump. Let's see. This little guy is for the gun. So also an ion gettering pump for the gun. We go to like 10 to the -9 torr on the gun, 10 to the -7 to 8 torr on the column, which is pretty high vacuum because we have a fed, and we'll talk about that in a minute. And then, that jumped in there. We'll have to come back to him. This is the turbo pump. So that itty bitty little guy, he's just a cute thing. He's like that big. That does all of the turbo molecular pumping. So that's our first rough pump, and then our second rough pump, let's see if we can get there, is down here. This little guy is a roots pump, Pfeiffer vacuum, oil-free roots pump. And that's it. There's no other vacuum systems on this machine. It's beautiful, especially if you ever worked with machines that had that, because used to be you'd have a separate room full of vacuuming equipment, and then you'd have these giant cinder blocks that you send your pipes through to keep the vibrations from going across to the other side. But we also have a magnetic field cancellation system. So that's this guy right here. It controls these loops. There's 7 different loops, 1 on each face and then 1 in the center. And what that does is there's sensors as well. I think in one of the previous images you can see it. There's these little green boxes that sit inside. There's 2 of them. And they sense magnetic fields, and then we actively cancel them with these loops. And right now the cancellation is on. Normally it would be about 30 to 40 nanotesla's peak to peak, which by the way is actually okay for a TEM, but we can take it down to, this is on the high end, it goes between 4 to 8 peak to peak. In the Y direction, there's practically nothing. I think that's because there's the cabinet right behind it that's kind of blocking everything.
And the reason is they gave us a room which is next to the magnetic resonance.
Yeah, we're right next to the NMR lab, by the way. So when you put your sample in, because we're at such a high vacuum, all of the stuff that's on your sample, things that are just gathered from the air, moisture, all that's going to start evaporating. And if it were to evaporate and not have anywhere to go, it would end up in the IGPA, the gettering pump. And we don't want to do that because there's only so much gettering the gettering pump can do before it has to be recycled. It has to go through a heating and all kinds of stuff. And you don't want to do that very often. So to protect it, we have this cold finger. And so you can see this copper braid, and there's a copper rod that goes inside, and then there's this little shroud that goes around where your sample comes out. And so anything that off gas is, most of the time, is going to go and it's going to condense on that cold finger. And then what we do is every night when we get done, we put it in what's called a cryocycle, where it runs the turbomolecular pump for 10 hours and lets that cold finger heat up so that it sucks all of the moisture out of there. And at that time, the ion gettering pump is turned off to protect it from the moisture itself. Let's see what else we got. This is where we load the samples. It's pretty nice. Like I told you, the single tilt holder is kind of a misnomer because the single tilt holder doesn't do anything at all other than just hold your samples. You just call it a holder. The tilting actually happens right here in this motorized stage that you put everything into. And so this can tilt 60 degrees as well. So we can go 60 degrees in both the X and Y directions, or alpha and beta is what we'll call them. And it's really great. We can do a lot of stuff with that. It didn't used to be that you could do that because the pole pieces, which are part of the lenses, they used to extend down and they were really close. Over the years, they've gotten better and better. And so now you have more space in between there. And so it's easier to get these high angles tilt going on in your sample. So the room that we use, you saw the microscope room, we don't altogether get rid of having a support room with this microscope. It still needs some help. So this is a liquid chiller. So we send water through the microscope continuously to cool everything down, the optics, all the computer boards, all that kind of stuff's cooled. And I think some of the pumps are cooled as well, the little turbo pumps, liquid cooled. And then we have battery backup systems in case something should happen. And because it comes from Europe, we have to use a transformer to get the voltage just right. We also, the tank, the high temperature tank that we showed you earlier that produces 200,000 volts. You think, like what kind of an insulator are you going to use for 200,000 volts? A lot of us are thinking, Teflon maybe or something like that. Actually, they use sulfur hexafluoride. The gas itself is quite a good insulator because it's completely satisfied with all that fluoride, so it doesn't care about the electrons or anything. So it makes a great insulator. That's what we keep here on hand just in case we have to change something out. And then we have nitrogen that supports the system and compressed air. This is a new plasma cleaner that we just got fairly recently for $5,000 off of eBay. It's a $50,000 machine.
You say that's a plasma cleaner?
Yeah, this is the Fissione 1020 plasma cleaner. And so the only thing that's keeping us from using this right now is we're waiting on a 25% oxygen, 75% argon tank. And for some reason, it's taken 6 weeks to get it because it's all backed up in California. So one day.
That's to clean the sample, no?
Yeah, so what we do is that oxygen argon mix in the plasma over the top of your sample. When you create that plasma, what it's going to do is it's going to oxidize any hydrocarbons that are on there, and then they'll turn into carbon dioxide when they get out of there. It operates at a fairly high vacuum. kind of 0, 1. It's like millitor, less than a millitor kind of thing. So yeah, hopefully it works. We haven't been able to try it out yet because we don't have the gases. And if we were to turn it on and try to do it without the gases, we could burn it up. So it's kind of a problem. One thing that you don't realize unless you've purchased a lot of TEMs is there's a ton of crap that you just have to keep in case they come back to fix your TEM. This whole rack, this is all just stuff that came with the TEM that we have to hold on to in case the repair people need to come back and do something with the machine. So if you're interested in buying a TEM in the future, you should know this. So my one regret in all of this is that I didn't take pictures of the room beforehand because in the words of some interesting people, this is what it was. Oh, come on. There you go. So the room was scary beyond all reason when I got there. It was terrible.
We have a lot of photos.
Oh, I need to talk to you about that because I want to get some documentation on
The
that.
right price.
I have like 3 giant wooden crates full of just trash, old machinery, tons and tons of stuff. But now on to diffraction. So I wanted to get everybody to, it was an interesting goal to have coming into a seminar. It looks like, when does this end?
But you have a, right now, but, no,
Okay,
go ahead, you have.
it's all pretty pictures from here on out. I guess that's what it's been the whole time. So I just wanted to get everybody excited about diffraction. So I have, my $20 tape measure from Home Depot, a cardboard box, and then this is a calibration slide for a microscope. It's just a normal optical microscope calibration slide. And so what I wanted to do is I wanted to say, how accurate can I be with this, junk that I've got sitting around? This is the junk. This is a great tape measure, by the way. Could I actually measure the spacing of this little grating that's on here? And so what I did was I used a very expensive laser pointer. And I don't know if I can reproduce it to where everybody can see it, but if I shine it through there, you can see there's a little spot pattern that shows up. And then I got this little ruler I measured it with. And I didn't do a very good job of measuring, but good enough. So this is between 500 and 515 nanometers. I measured the distance between here and there to be around 338 millimeters. And the distance between those spots, I measured to be 17.5 millimeters. And so the nice thing about this is the angle is small enough that I didn't even go through I did actually go through the trouble of doing the tangent and then doing the sine of that angle and all that kind of stuff, the arctan. But it turns out you don't need to do any of that because it's a small enough angle, it doesn't matter. So all I got to do is do the 500 nanometers multiplied by 338 millimeters divided by 17.5. And what do you get? 9.7 microns. So I do the same thing with 515 just to see what my range is, and I get 9.9 microns. This little grating, if you look at it, it's 10 microns. So I can get, within, what is that? 300 nanometers. I can get within 300 nanometers of accuracy with a cardboard box, a laser pointer that's, part of a remote, and a tape measure. So that's the exciting thing about electrons. You can imagine we have a machine with a much smaller wavelength. So this is 515 nanometers. It's 200,000 times bigger than the wavelength, the characteristic wavelength of a 200 kilovolt electron. So here we're dealing with electrons that have a characteristic wavelength of 2.5 picometers. Here we have 515. And so these are some diffraction patterns that we were able to get. This is a cool one. This is quasi-crystals. I have to talk about Dr. Yakuman about this. Evidently, these spots follow a Fibonacci sequence. So it's like long, short, short, long, short. I don't know exactly what the sequence goes as. But this is a 5-fold symmetry, and that's why everything's kind of wonky on it. Instead, normally you'd see like 6-fold symmetry, and then it's going to all look really regular, like a honeycomb. But because this is quasi-crystal, it's got different, characteristics. And this is what we call a powder diffraction, or a ring. It's similar to an X-ray powder diffraction pattern, if you're familiar with that. You can measure these. These are Coochie lines, but you can't see them because the contrast is too bad on here. You can barely see these. And these are caused by diffuse electrons that create diffractive effects. We also call those incoherent diffraction, I believe, or incoherent electrons. Evidently, they don't know what they're doing. So measuring these, you can measure these distances and they're in inverse nanometers. So then you just got to do 1 over that. And that tells you what the spacing between planes would be to create those rings. So like this one is 3. So that's like 3 angstroms right there. Anyways.
These are rings of powder, right?
It's not actually a powder, it's polycrystalline. But what you get is powder characteristic diffraction. Here's another one that's kind of exciting. So Dr. Yakuman has had me hunting for carbines for the longest time, and they're really, really elusive creatures. But I was able to get this diffraction pattern the other day, and these rings are just about where they should be. So they're there. The trick is I had a really, really low dose rate here. And so we're working on getting everything set up on the microscope to be able to give it a low enough dose rate not to damage the carbines and be able to image them at the same time. We're going to get there. It's just, time. This is dark field imaging. So we talked about diffraction. You have your primary beam, you have your diffracted stuff. If you just get rid of the primary beam, you can get dark field. And that's what you do in an optical microscope. But in a transmission electron microscope, you can take it one step further. You can pick which one of those diffracted spots. Say you have, even in a polycrystalline, you can pick which ring you want to put your aperture around. And you can get rid of everything but that. And so in this particular case, what I'm doing is I'm highlighting crystals that all have the same orientation, and they're all the same type of crystal. And these are little intermetallic compounds that are inside a metal matrix. And so that's what lights up, and the metal itself doesn't really interact too much. This is just another image of, you can see there's like a boundary here between 2 different phases. And so the one phase is rich in whatever it is that we were selecting that spot. The other one is less rich in that spot. And so dark field imaging on a TEM is much more informative than it is on an optical microscope. So if you have things that you want to image, come to us, because we can do a lot of different things. And this is in TEM mode. You can't do quite the same amount of selection as you can in TEM mode. In STEM mode, but the contrast and the brightness is much better. These pictures take forever to do. So here's just another example of bright field and dark field at the same time. And this is STEM. The cool thing about STEM is you can take both dark field and bright field at the same time. We can change the camera length of the machine so that we can even, because we have 3 detectors, it's 3 rings. One's a sphere or a circle in the center, and then we have 2 rings around that. We can extend bright field clear out to all of those. So all 3 of the detectors are doing bright field, or we can take it all the way so that we're doing high angle dark field. And high angle dark field is cool because it gives you contrast in the Z. So like if you have gold and you have copper, you're going to see the gold interacting much more strongly than the copper because of that. Now let's just go through and look at some pretty stuff. This is a junction from Dr. Kambu. So some people in here will probably recognize that. Can't publish these papers in case you're like, these images are not for sale. Nobody can do anything with them. Just so you know, I can't, you can look, but we're getting closer in. So this is like what we were trying to image right here. It was difficult because this sample was old. Oh, hey, Alondra. She made these. These are really cool. So it's a silver wire with nickel around the outside of it. And you can see that in this image right here. See how it's much darker around the edges than it is in the center. And then you can see here's this the silver image, and this is the nickel image. So it's really cool. These are just fun pictures. Here we have a nanorod. You get some really nice contrast there. So you can see these are columns of atoms that you're looking down. These are some fun little particles that I think Jesus synthesized. And then you can see like, this could be stress, this could be a few different things. These contrast lines, they come from various sources. This is a really cool one because of its shape. Also, contrast is an interesting thing in TEM. Turns out the more contrast you have, the worse your focus is. So this is out of focus, this is closer to focus, and this is in focus. And it's kind of annoying, and you can do different things. You can put apertures in to change that characteristic. But when you're in focus, your contrast is going to be minimized. Here's a really cool one that Jesus brought in. You can see we've got this little head and then these tails, and they're all over the place. Really cool little nanorods. Here's one all by its little lonesome. This is just to show you what kind of resolution we can get on this thing. This is just a gold evaporated onto a standard, but you can see we're getting really good. Like you can measure the distance between these atoms, directly. This is silicon, and these lines are actually telling us thickness contours. So as it gets thicker, it goes through what you call extinction distances, and it'll go from light to dark to light to dark to light to dark. And you can see these little thickness fringes, and you can actually use them to measure the thickness of your sample. Or if you have a wedge, you can measure the angle of that wedge point coming to the edge of your sample out. So there's a lot of really cool things you can do there. Here's another one. Yeah, we'll just keep going through. Flower. Actually, this is some fun stuff, but it looked like a flower to me. There was another one that didn't end up in here, but we had one that looked like a grasshopper leg. So my joke got ruined because it's not in there.
Question for Blake and yes, please. The tip of the gun, the field.
Oh yeah, I was going to come back to that.
That's very important because it's a field emission gun. It's a
Yeah,
very
yeah, yeah.
bright gun. Anyway.
So the old microscope that you might have been using has this guy, and it's the worst of the three. It should, and it could have one of these, which is a VA6, but it doesn't, which is much brighter. Instead, we have this guy, and this is a FEG, so field emission gun. The tip is so tiny at the tip that when we apply the excitation or extraction voltage to it, the field is high enough that it straight up just pulls the electrons out. There's different kinds. You can have a cold, or you can have a heated tip, and I believe ours is cold, right?
Yes,
Yeah, it's a cold emission, and that's going to give you the best
very
characteristics.
coherent,
Yeah, the coherency of your electron beam is entirely dependent on the size of the source that the electrons come from, and that's spatial coherence. And so you can imagine all these little electrons are marching down the column in step with each other because they come from such a tiny spot. And that leads to much better images. In some of the images you might have noticed there's rings. The more rings you have surrounding your image like that, those are coherence rings. And so you can tell when you have a very coherent electron beam versus a non-coherent. Non-coherent, you won't see any rings. Very coherent, you'll see lots of them.
But let's say, John, please go ahead.
Is this used by anyone in the department?
Well,
For now.
for now. But yes, bring your samples by. We're in the honeymoon period right now of the TEM. So at some point it will become a core facility or something like that. We're not going to be able to have the cake and eat it for free all of the time. But for now, yes, you can come by, bring some samples. We'll take a look at them. We want to really get the word out. We want people to know that, we've got a class, a state-of-the-art machine on campus. And it's only just the beginning. Like, we've got a few toys here and there that we've ordered with the machine, but we got so much more coming. So we'll have drift correction, we'll have liquid stages that we can do things, environmental stages we can heat stuff up with. It's going to be pretty fancy.
Go ahead. please.
Why don't you just drive to California and pick up that thing?
The gases in California,
Been in California for 6 weeks.
because they're in the docks and
Swim out.
he said the union on the docks. Jorge.
It was like a big red button to the operator table. What's that for?
Oh, don't hit it. I did once. Actually, I didn't hit it. I disconnected it, and it turns out if it's the same as hitting it. It just shuts everything off. Boom.
Case of the emergency.
Yeah.
What kind of tamales did you make?
Ooh, the good kind. There was a nice red pork tamale. I used a white corn masa. It was the fine stuff, the nixtamel.
And let me tell you something before we close. The idea, this is an APS, IPMS instrument. Okay? Of course, the university wants, we have to pay for the service, and the way to pay for the service is to charge. But right now, we are using that. Blake is really getting familiar, also Alex and other people. So the idea is he will train you to use the mouse, okay, by yourself. Once that you are confident, you just sign online and you use it. Okay? And then for now, please go to use it because we need to demonstrate that a lot of people might. Please,
For the training, is there like some sort of certification that we could do so that we could put on our resume?
well, let me
I'll
tell
put one for you.
Blake is can train you on the use the mic. I am going to offer a short course next semester on kind of 2 weeks course on the basics of electron microscopy. So you take that, then you will have a proof that, but basically Blake will train you.
Yeah.
I would say using a microscope is like playing an instrument. You have to be there and then use it many times until you get confidence. Yes. No.
Oh, no, that's after we get done. So, so at the end of the day, when the liquid nitrogen, because we keep liquid nitrogen on that trap and it lasts for 6 to 10 hours. So at the end of the day, I'm not coming back in the middle of the night to fill it up again. So I take it off of there, the cold finger starts to warm up. We start what's called the Krauss cycle, and then it uses the turbomolecular pump instead of the ion Gettering pump all through the night until all of the, water vapor and different things that have gathered on that cold finger have been removed from the column. And then the next day, all you do is you're ready to go, because once it ends on its own.
But once that you have your sample in the order, it takes a minute, no?
Yeah, we'll put your sample in. We let it sit for 2 minutes under vacuum before we fully insert it into the column. And then from that point on, yeah, depending on, it takes a few minutes, we get the Z height right. Once we get the Z height set, we set it to what's called eccentric height. And then from that point on, when a lot of these pictures were actually done really quickly, because Jesus would bring in 6 samples and we would go through 6 samples in an hour's time and get 10 or 12 pictures of each one. So.
And I have to say something, this microscope can be operated remotely. So if you or your advisor buys a remote station, it only costs $10,000. So you can do it from home. You don't have to, somebody has to load your sample. Good, okay, thank you very much.